To the Max School, Quantum Espresso Max School. Good afternoon. So it's a great pleasure for us to have this special guest lecture by Professor Stefan BLÜGEL. Thank you, Professor, for accepting our invitation. So let me briefly introduce him. Professor BLÜGEL obtained his PhD in physics in 1988 in Aachen University, followed by a postdoc position at the University of Tokyo in Japan. Since 2002, he is director of the Institute of Solid-State Research for Zentrum Jülich at the Department of Quantum Theory of Materials, and he is also professor for theoretical physics at Aachen University. He received several prizes and honors, such as the Friedrich Wilhelm Prize at Aachen University, Heinz Meyer-Leibniz Prize for Excellent Achievement in Research Work. He is now leading an ERC synergy grant about three-dimensional magnetization textures. So his research interests are mainly about computational physics in electronic properties of real materials, in particular spin-orbit-related phenomena in 2D materials, topological insulators, Rashba effects, Hall effects, skyrmions, and many other topics. Professor BLÜGEL is a worldwide recognized scientist in computational magnetism, as shown by his publication track record. Just a few numbers here. He is author about 520 publications, and many of them on Science and Nature top journals, with H index of about 72 and cumulative citations about 22,000. So today, he will speak about ab initio Spinorbitronics, how the tiny spin-orbit interaction saves energies in information processing. So I leave the word to Professor BLÜGEL, and I'm very sure that we will all enjoy his talk. So thank you very much.
Yeah, thank you very much, Alessandro. I would like to start my talk thanking my chairperson, Alessandro, for the nice introduction, and the organizer of the Max School for Advanced Materials in Molecular Modeling with Quantum Espresso for the invitation. It is my true pleasure to present this lecture, because I really think that you are the next generation in this world that carries on all the things into the future, at which many people of my generation and the previous generation spend their entire scientific life on, including Stefano Baroni, which you heard this morning, and myself, for example. It is a true pity that we cannot meet in person here at the wonderful place of Trieste. Yeah, I really enjoy the Italian espresso, and I think it would be good to have a real Italian espresso after the quantum espresso. Oops, wait a second, how to continue? I really think that you are the rather diverse community who is attending these lectures that are interested in many very cool problems. And maybe some of you have never heard about the word Spinorbitronics before. But you maybe notice the word spin-orbit coupling in this word Spinorbitronics. And the Spinorbitronics is a compound word actually developed by Albert Fert for spin-orbit coupling and electronics. So the spin-orbit coupling, maybe you vaguely remember from your lectures at your university. The spin-orbit interaction is the coupling of the spin degree of freedom to the orbital motion of the electron. And the orbital motion of the electron in a crystal means, of course, the crystal motion, the motion of the electrons in the crystal. So maybe you remember this form here of the spin-orbit interaction, which is the coupling of the orbital moment to the spin moment. And I have written it in the radial symmetric form. You might have seen other forms, but this is the radial symmetric one. And maybe from the atomic physics, you remember this interaction best. You see here the velocity of light, the speed of light, and obviously it is a relativistic effect. And this tells you already that this is probably a very small effect. But maybe you don't consider this to very important. Often this spin-orbit coupling in the literature is simply abbreviated as SOC, because spin orbit coupling, to write it all the time and to speak it all the time is a little bit hard. So when you hear SOC, it is the spin orbit coupling. Maybe you have seen a key in the ESPRESSO code or ESPRESSO configuration file, and you may be able to switch the spin orbit interaction, the key of spin orbit interaction, on and off. And yeah, maybe you have switched it already on, and you see hardly any difference between switching on and switching off. And this I have done for you. So I have calculated here germanium without spin orbit coupling and germanium with spin orbit coupling. And if you look at it, it looks really nearly like the same. But if you look a little bit careful, and with spin orbit interaction, you need good eyes. If you look a little bit careful, you see here, just at the valence band maximum or minimum, you see here that here you see basically suddenly a small spin splitting, band splitting, which you have not seen here. So if you look very careful, you see here the empty band, you see here the valence band, and the valence band splits off into a split off band here, and a heavy hole and light hole band. And now you may say, yeah, this might be 100 milli eV. This is nothing. No, that's not true, because 100 milli eV are already 1000 Kelvin. And if you remember that maybe many transport experiments are maybe done at 10 Kelvin or at 70 Kelvin or at 200 Kelvin or at room temperature, on the level of these experiments, 100 milli eV is a huge number. So we're dealing here with small numbers, but we're dealing here with numbers which are absolutely irrelevant. I would like to come to a second example. And if you do not understand everything what I'm saying today, it is no problem, because next week, Alessandro, our chairman, will give you an introductory lecture to the subject. And maybe I give you a little bit more an overview while he goes into the nitty-gritty details and explains you all the details. So here I show you another example, which is the band structure of ferromagnetic iron. Iron is ferromagnetic, and maybe you remember, then you have a pair of bands which are basically the same, but shifted by a certain energy. So for example, you see here these black bands, and you see here the red bands. And you see here the band structure of these dx and dy states, dxy and dyz states. And you see that these states again here. These are the minority states, and these are the majority states. And between we have an energy difference, which is basically what we call the exchange splitting. Everything is super fine. Everything is great. But now we switch on the spin orbit interaction. You know, if you look at it, first of all, it looks rather the same. You have here the bands here. You have here the bands here. You have here the bands here. But if you look a little bit more careful, you realize, yeah, okay, without spin orbit interaction, spin up and spin down states are eigenstates of the SZ operator. But with spin orbit interaction, that's not true anymore. Spin up states and spin down states can mix. And for example, you see here, you have here a state here, an unoccupied state here, which has a crossing. This is the state between the dx and yz. And here you see you have the same crossing. But the equivalent state here has a gap opening. And the same happens here, for example. Here you have a crossing between the majority state and the minority state. And exactly at this crossing, you have here an opening, but you have no opening here. Please notice this band structure is plotted along the gamma H line and the gamma H3 line. This is this line from gamma H to gamma H3. These are basically, the crystals is identical. But what you do now is you have a magnetic structure, and due to the spin orbit interaction, you translate the magnetic structure into the crystal structure due to the spin orbit interaction, and you break the symmetry. You break the symmetry of the crystal. Your crystal looks cubic, but in reality, it becomes tetragonal. And what you see is then suddenly, due to this magnetization direction, the electronic structure along this direction and the electronic structure along this direction is different. And you see this tiny gap opening. Now you say, what is this tiny gap opening? Who cares about this? But what happens is, due to this gap opening and to the fact that the easy exit, that the magnetization direction has different band structures, it means also that different magnetization directions have different energies. And there is suddenly one magnetization direction relative to the crystal lattice, which has a different energy than the other magnetization direction with respect to the crystal structure. And this we call the magnetic anisotropy energy. The energy scale is about 0.5 to 1 millieV, not EV, millieV. This is not a typo. So remember, this morning, Professor Baroni has talked about phonons. This is also a small energy scale, but this phonon energy scale might be in the order of 100 millieV at the preon zone edge, or 200 millieV at the preon zone edge. Here we're talking about 0.05 or 50 micro EV to 1 millieV. And here you see a totally over-exaggerated picture of the magnetic anisotropy. So you see that in this, the length here is the energy. You see in certain energy directions, like the 110 direction, in this particular case, the energy is high. And in another direction, the energy is low. And therefore, this is the magnetic anisotropy energy. And now you say, what is the importance of this very small number? This is a very important number because it is important for all electromotors. So a modern car, like an e-car, has about 200 to 300 engines, electrical engines in the car. So you want to move the window, you want to drive, you want to use the wiper blades, you want to change the mirrors, everything has motors. And these motors require a core, a magnetic core, to save energy. And this magnetic core needs a certain material which has a certain magnetic anisotropy. We call that magnetically hard material. The same materials which you have in your headphones. And there is a huge interest in these materials, and there is a huge activity worldwide to produce the right material for the right energy scale, the right temperature scale, environmentally appropriate. So this is a huge field, but I'm not talking about this field today. I only want to make you aware that 50 millieV or 50 micro EV or 1 millieV can change a total perspective of an entire industry. So this spin orbit coupling, maybe you never heard of, maybe you have never interested in, has fascinating realizations and ramifications in a solid, and has also attached to it are also fancy names of interesting people, like the Rashba effect, the Dresselhaus effect, the Edelstein effect, the magnetoelectric effect. We talked about the magnetic anisotropy. Related to these are the orbital moments. We have a spin orbit torque. We have the Jalochinsky-Moriya interaction. We have chiral magnets and skyrmions. We have all the Hall effects, the anomalous Hall effect, the spin Hall effect, the chiral Hall effect, the quantum Hall effect, the topological spin Hall effect. We have topological and Chern insulators. We have spin relaxation mechanisms like Elliott Jaffet and Dirk Knopf-Berell. We have the Gilbert damping. So there is an entire zoo of phenomena which are in this way or that way of great relevance, which hinge on the spin-orbit interaction. And I cannot explain all this in my lecture, but I would like to make you aware that based on this spin-orbit interaction, there is an entire field which we call the Spinorbitronics. And for example, the spin-orbit interaction is finally responsible for creates an interaction between atoms, between the spins of atoms, which is the Jalochinsky-Moriya interaction. This Jalochinsky-Moriya interaction can form chiral magnetic textures. One of them is the chiral magnetic skyrmion. It's a finite size object of 10, 20, 30 nanometers and behaves like a particle. It is ultra robust, and have a very efficient electrodynamics or a very efficient dynamics. And this, there is the hope that such an entity may be an entity for an information carrier, with which you can store information. Then, of course, this is very robust because it has a topological nature. It can be described by a topological, non-trivial topological invariant in the real space. But the spin-orbit interaction is also responsible for materials which have topological invariance in the momentum space, in the electronic structure. They produce, due to the surface bulk boundary correspondence, they produce edge states and surface states, which are also topologically protected, and therefore they are very robust and have a very small resistivity. They can be described by the topology in the momentum space. But there's also an effect which we call the spin-orbit torque, which is described by the topology in a mixed space, in the momentum space and in the spin space. And this spin-orbit torque is a phenomenon which is, if you drive a current through your system, you produce a magnetic torque on these chiral spin textures, for example, and it allows you, for example, to move this chiral spin texture with high speed. And you don't need for this an external magnetic field. So that you can basically integrate that into a technology. And you need very little power. It is scalable to a device. And this allows you the manipulation of this skyrmion. It allows you, this topological materials allows you to control the detection of the skyrmion. You can count satellite skyrmions which go through a wire. And this, at the end of the day, you can build up an entire technology on this with low power consumption, topological robustness. You can even go into Majorana fermions and quantum computing. So this is the big scope of the Spinorbitronix. And in this lecture here, I will pick out a few things to give you a feeling for the field without going into all the details. Spinorbitronix fits into a technology based on magnetism, which already exists. And maybe you know that I would say 90% of all information worldwide is stored on magnetic hard disks. It is cheap, it has a high capacity, it's extremely reliable, and it is capable of further developments. And without this hard disk, all this cloud computing would not be possible, because the hard disk is where all these big data centers are. They are using this hard disk. Of course, not these small ones, but use hard disk farms. And if you look at basically the shipped capacity in exabytes, you see that the hard disk, which is this blue section here, is basically it is still expected to grow. And what you also see, it's a huge fraction that all the information is stored on this hard disk. And what we realize is there is also a Moore's law for digital data. The doubling of the data, of the created data, increases every 2 years. And therefore, even now, you have already 10% of the worldwide electricity use goes for information technology. If you think about computing, you probably realize also that computing takes quite an amount of energy, and the size of the computers which we can afford are actually limited by the electrical power. So there is a strong motivation to develop a technology where we can take data from a memory into a compute unit or store data on a device with much less energy. And therefore, we need novel paradigms for energy efficient memory and computing. And these skyrmions, which I'm talked about, they might be a path to this to disruptive change in the information technology. So how could you think about a skyrmion? Think about a ferromagnetic state. So this red thing is a ferromagnetic state. And And on this ferromagnetic state, think of this ferromagnetic state like an ice hockey field. Of course, not everybody in the world you have seen an ice hockey field, but maybe on TV. So you have this ice hockey field, and in this ice hockey field, you have an ice hockey puck, which is a hard rubber disc. And this hard rubber disc resembles these fermions. And if you have this spin orbit torque, they run around here on this ice hockey field. But these fermions are not arbitrary magnetic structures. No, they are topologically protected magnetic structures. And what happens is that each magnetization points in a unique magnetization direction. And you can put now these fermions on basically on a memory, which is not a hard disk memory, but a racetrack memory. And then you have, then you can save in normal, you can use that type of register type memory to save enormous amount of energy. And the unique properties of the magnetic fermions is that you have nano-sized particles which guarantee high data density. They are topologically protected. They, provide thermal stability, and they are very fast. This requires, this enables high data flows. And you can also use the two-dimensionality because you can not only go in one direction, but you may go in various directions. And so these properties give you an idea of a new generation of magnetic memory, which is the solid state memory. So no mechanical parts are moving, and therefore it would be a low power memory. And you can also do programmable logic with this memory. So you can reconfigure the memory to have different OR and XOR structures. You can do that massively parallel for in-memory computing. And what is a great advantage is you can also do it, you can also use this object for neuromorphic computing, which guarantees low power consumption. And it is a scalable architecture. So there's a lot of future into this. But now, before I get carried away by all these possibilities which we have in the future, I come back a little bit more to the basics. I remind you, if we have a non-magnetic state without spin-orbit interaction, you may have a band structure of a certain band on a certain K vector. And these are typically Bloch states. And these Bloch states are true for degenerate because we have a spin up and a spin down state with the same energy. But if you switch on now the spin-orbit interaction in your code, then you will realize that this spin up and spin down are actually not good quantum numbers. Instead, due to the spin-orbit interaction, you can mix the spin up and spin down states. But of course, the spin-orbit interaction is small. So we call this one state spin up because most of this state is spin up, although there's a little bit spin down. And we call a spin spin down because most of it is spin down and there's only a little bit spin up. And so basically this factor A is large and this factor B is small. And this is called the Elliott-Jaffet parameter. And actually, since the spin-orbit interaction is a small quantity, you feel you can do perturbation theory. And what enters in this perturbation theory is the spin-orbit interaction. And this, of course, you remember that you have this sigma, these Pauli matrices, and you have off-diagonal elements of the Pauli matrices which are responsible for the spin flip matrix elements. So you have a spin here, maybe a spin up, can flip into a spin down due to these off-diagonal elements of the spin-orbit matrix. And in some instances, you have crazy Fermi surfaces. And in some instances, you have so-called hotspots where this denominator becomes very small. And this prefactor here, B, becomes suddenly very large, maybe 50%. And this determines the lifetime of the of spins. So if you if you imagine you have a solid, here, for example, osmium, and then you have a spin current. Somebody externally produces a spin current for you. For example, you run a current to magnetic materials, then you have a spin current. And you put the spin current into the solid. Then the spin orientation matters. And you see that in some areas, if you inject the spin like this, in some areas, you have so-called spin hotspots where this B becomes very large. And if you integrate now all this B over the Fermi surface, you get the inverse of the spin lifetime. And I'm saying in this configuration, the spin lifetime is roughly 1/20. But if you have now another configuration, for example, you shoot in your spin in a different configuration with a different magnetization axis, so you have a different spin current, then the same Fermi surface will produce at other places a spin flip hot area. And then you can do it the same. You integrate now this Fermi surface, which is the same Fermi surface, but the matrix elements are different on this Fermi surface. And then you see suddenly your lifetime has changed. It's not only, so the inverse of the lifetime is not, or the lifetime is not 20, but here the lifetime is 13. So it is much, much smaller. And therefore you have a giant anisotropy in the lifetime of a spin current. And this, you can now think of a Gedanken experiment or a real experiment. So imagine you have here a magnetic material, and this magnetic material has the spin polarization pointing up. Now you run a current through that system, and the current through that system, electrical current, goes through that system and becomes spin polarized. And now you have a spin polarized current entering a non-magnetic material, for example, this osmium. And then you have a spin current in this circle. But parallel to this, you have a diffusive current, which diffuses into your solid. And now you can detect this current by your detector. So what you do is you measure the voltage difference as function of the position. And this I basically have done for you here. And you get such a curve because you get a typical diffusion behavior. And the diffusion length depends on your spin lifetime. And now you can do the same for a material with a different direction. And what you will see is that you get a different lifetime. So that means basically you can polarize spins. You get a spin diffusion, which is different for different directions of the spin current, or polarization of the spin current, I should say. So this was one example. But let me come back to our the importance of spin orbit coupling in relation to the inversion of the spin inversion symmetry. So imagine you have spin inversion symmetry, or space inversion. Sorry, you have space inversion symmetry. Then you can show that these two wave functions are corresponding to states. These are Bloch wave functions corresponding to states which are degenerate. This is this particular case. How do you prove this? You take this wave function here, you apply time reversal symmetry. That means you have to take this Pauli matrix sigma times minus I times the conjugate. And what it does for you is your time inversion means k goes to minus k. And you also have to flip the spin. Time inversion means spin flip. You go from here to here, and you go from here to here. And now you remember that you have space inversion symmetry. You go from k to minus k. And you're ending up at this Bloch vector again. And you end up in the wave function with opposite spin. So these two are totally degenerate. Or the energy, the state is totally degenerate. So what I have shown you is that for time reversal and space inversion symmetry, the energy of the K point spin up and the energy of the K point spin down is the same. But if you break this space inversion symmetry, then it is not anymore the case. Because then you have time reversal symmetry only. And the energy of K spin up is the same as the energy of K of minus K spin down. But the energy of the eigenenergy of K spin up is not the same as the eigenenergy of K spin down. So that means if you are now looking at a particular K point, the degeneracy of spin up and spin down states is lifted. What does it mean? It means this electron, maybe this electron might have never heard about the spin orbit interaction. But what this electron understands is that its counterpart, the spin down electron or the spin up electron, has not the same energy for the same K point. In other words, the spin orbit interaction produces locally a K-dependent magnetic field, a K-dependent magnetic field omega of K. And that is very important to realize that if you have a broken space inversion symmetry, your spin orbit interaction has the feature of a local magnetic field in your solid. And this local magnetic field is very large. So a typical example of a broken space inversion symmetric situation is the surface. On the surface, you have electrons running around the surface. Maybe they are delocalized. They are wonderful. They are characterized by the K parallel wave factors. Everything is fine. But I would like to remind you that we have in this surface, of course, we have our Coulomb potential, 1 over R potential and exchange correlation potential and electron-electron interaction. But we have these basically symmetric potentials here. But if you come closer to the surface, you have this symmetric potential is broken. And what you have is a finite gradient of this potential. And this finite gradient produces the gradient of a potential is something like an electric field. And this electric field in the rest frame of these electrons, they don't think about this electric field. In the rest frame of these electrons, this electric field is Lorentz transformed. It becomes a B field. And this B field interacts with these spins of the electrons. And this produces, besides the original interaction of the electrons, an interaction which has this notion here. It is a spin orbit interaction. The effect is called the Rashba effect. And basically what you see here, you couple the spin degree of freedom to, this time not to the orbital motion, but to the kinetic motion of the electrons. And this is also a spin orbit interaction. And this parameter here is called the Rashba constant. And this Rashba constant depends on the spin orbit strength, the asymmetry of the wave functions, the orbitals, and the essence of the S, whether it's S or P or D, and so on. And this is, of course, our motivation to understand the strength of this Rashba effect. And here I show you now an example. This is basically the Rashba effect on the gold surface, gold 111. You see here the bulk states, which are totally unimportant. You see the famous L gap of this particular surface. And what you see is here the surface states, and you see that the surface state, the degeneracy of the surface state is lifted, except for K equals 0. And here is the corresponding experiment to it. I think it's from Reinhardt. It's a photo emission experiment. And you please notice the scale here and the scale here is slightly different. So basically I rescale here this experiment, and in photo emission you can only see occupied states. So you see here, it is a good comparison between theory and experiment. And if you look a little bit more with a zoom into it, You see, you have here a degeneracy at each K point. The degeneracy is lifted. You see here you have you have a relation between the spin and the momentum. Here you have the spin up states. Here you have the spin down states. And here it's exactly vice versa, because this here is the spin down state and this here is the spin up state. So basically you have a spin momentum locking. Now this spin momentum locking has great consequences. I should say first, so where is actually this rush bar strength coming from? Now, I think if you look a little bit more carefully on the surface, of course, in reality, you have atoms on the surface, not only homogeneous electron gas where everything is smooth. You have atoms on the surface. Or maybe we can circumscribe these atoms by spheres. We call this a muffin-chin sphere. And in this sphere, you have this 1/r potential here, and other contributions too, exchange and correlation, and so on. But you remember that this spin-orbit interaction is somehow related by the strength proportional to the derivative of the potential with respect to the gradient of the potential with respect to the radius. And now you should think the following. Your wave function has a tail and has a head. The tail is always out there in the homogeneous electron gas, as a Bloch wave vector, is propagating, but it has also a head. And this head feels this 1/r potential, and it has strong oscillation here. It means it feels the depth of the potential. It's running around like crazy and producing a heavy mass and producing this spin-orbit interaction. And sometimes these electrons is far away with a certain probability in this homogeneous electron gas picture. And in some probability, it is in this tail where it sees this strong spin-orbit interaction. And if you put this all together, you can ask yourself, where in the hell is the spin-orbit interaction created? And then you see 99% of this spin-orbit interaction comes from a very small region around the atom. And I've plotted this here. As you see here, a typical sphere radius might be 2.5 atomic units. And you see 99%, or close to 90% or 99%, you have already at 0.3 atomic units of the sphere. So it's the radius might be 10%, the volume might be, I don't know, 1,000. This you should keep in mind. And then the next question is, I told you it depends somehow on the gradient of the potential. That is true, but it depends also on the asymmetry of the wave function, because at the end you have to calculate matrix elements. And therefore you see the contribution of this rush bar parameter here, or of this spin-orbit strength, or maybe better the rush bar parameter. You see 60% comes from the surface atoms, but the other 40% come basically from deeper lying atoms. So you have some depth profile which contributes to the rush bar effect. So why I'm telling you all this on the rush bar effect? Because it has a strong implication to magnetic interactions. And this I would like to discuss with you now. This is the Dzhalodzinsky-Moria interaction. The Dzhalodzinsky-Moria interaction, I would like to discuss now. What happens is, imagine you have two atoms on the surface. And if you have two atoms on the surface, and you have your conduction electrons, the atoms are magnetic, they have a local magnetic moment. The electrons come, the electrons scatter on these electrons, on these atoms with this spin. The electrons propagate to the other side, to this second atom, and maybe they propagate back. And this propagating to one side and propagating back, this causes an interaction, and this we call the Heisenberg interaction. And this we can formally describe something like, yeah, the interaction is the conduction electron scatters and is propagated, it scatters, it's propagating back, and this leads to the interaction. But if I have now rush-by electrons, then I get an additional term here, and these rush-by electrons, due to the fact that these rush-by electrons have a certain behavior due to the spin-orbit interaction, produce an additional term here, which is this Jarodzinski-Moria interaction. And let me remind you, the symmetry breaking of this at the surface produces these rush-by electrons, and therefore these propagating electrons have not only a term which comes from the ordinary electrons, it has also a contribution which comes actually from the spin-orbit interaction of the rush-by electrons. And so you have here these Greens, we call this the Green's function. You have here the Green's function twice, and the spin-orbit interaction twice. Spin-orbit interaction is small. The square of the spin-orbit interaction is even smaller. So that means, forget it, you only stay to linear terms in the spin-orbit interaction. I can write out the linear terms in the spin-orbit interaction. I remind you at the fermionic rules of Pauli matrices. So sigma times A and sigma times B gives you AB and sigma cross B. And if you put that in, you see you get this term here. But this looks like this term. But you also see you have a propagating term from 1 to 2 and from 2 to 1. And they don't cancel because propagation of a k vector means propagation of a minus k vector, and the spin is down, and therefore it adds up. And this gives you exactly the remaining contribution here. And we can not only also get this algebraic form of the Jarodzinski-Moria interaction, we can also get a description of the Jarodzinski-Moria in terms of the electronic structure. So what I have shown you is the spin-orbit interaction in combination with the structure inversion symmetry produces a new interaction. And this new interaction we call a chiral interaction. Why? Because if you look at the magnetic of this pair of atoms with this particular magnetic structure, you see that the cross product of this points in the y direction. So maybe this is the direction towards you. Whereas if you rotate, so here the spin structure is rotating clockwise. But here, the spin structure is rotating counterclockwise. And in counterclockwise, this cross product maybe points into my direction. And what you see is, if you rotate left and if you rotate right, has a different energy. And the difference in the energy depends on the sign of this Jarodzinski-Moria strength. And the sign of the Jarodzinski-Moria strength depends on the details of the electronic structure. So I have showed you that the break of the inversion symmetry is a path to chiral magnetism. And of course, we had to learn a lot about this strength of the Jarodzinski-Moria interaction as function of the electronic structure and so on. And this Jarodzinski-Moria interaction, is really the path to chiral magnetism, which you can see, for example, that ground states become, the magnetic ground state can become a spiral because if the chiral interaction is strong enough, the ferromagnetic state is not anymore stable, and you have a chiral, you have a spiral which spirals only in one-handedness. In this case, for example, counterclockwise, whereas the mirror image, where the magnetization spirals clockwise, does not exist. And here's an experimental proof of this situation. It's also responsible for, these are one-dimensional magnetic structures. It's also responsible for the two-dimensional magnetic structures. And here you see an example of a skyrmion, which is calculated and measured experimentally. It is also responsible for chiral domain walls. These chiral domain walls are extremely stable because they don't flip to the energetically equivalent one, and therefore you can move it with high speed. It is also responsible for it also changes the magnon dispersion. Basically, you have a non-reciprocity in the magnon dispersion. A right rotating magnon and a left rotating magnon has a different dispersion. So now I'm looking a little bit at the time, but maybe we have still 10 minutes. We started a little bit later. So let me say a word about this skyrmion simulation and description. So I have introduced to you, without much ado, this Heisenberg interaction, this Jarodzinski-Moria interaction. I mentioned the magnetic anisotropy. There are also some other parts which are currently not of my interest. Which is a dipole-dipole interaction. And, basically, if you have calculated all these parameters, Jij and Dij and K, then you can put it into an atomistic spin dynamics program, and you can calculate all these magnetic structures, and you can simulate the lifetime and the dynamics and all this. And you can do it even on your mobile phone. You can download this code. It's free for you, and you can play with it. Originally, the code was made for a high school teacher, but the experimentalists liked the code so much so that we developed this code further for playing and with this spin dynamics. But sometimes it is all this spin lattice models is a little bit complicated. You want to do also some analytic work, and therefore you often go from this atomistic spin model to the micromagnetic spin model. And this you can do if you, for example, take a long wavelength approximation. You take the magnetization at point J, look at the magnetization at point J and expand the magnetization at point I, and you do a Taylor expansion. And then you come basically to this micromagnetic model. That is well known. It developed in the 60s. And of course, we all want to relate these parameters A to these parameters G. They are related due to these approximations. But at the end, of course, we want to calculate these quantities from first principles. And so there are methods and ways to relate the total energy, which you can, as function of the rotation of the magnetic structure. For example, you introduce a spiral, and the spiral changes the energy. Like in this behavior, a spin spiral with a certain Q vector. And then you can basically calculate the spin stiffness, which is this A, and you calculate the derivative of the energy with respect to Q, gives you this Jarodzinski-Moria strength, which we call here the spiralization. And you can calculate the magnetic anisotropy, and you will learn this, how to do that next week. And then you can, for example, calculate these your parameters, or you can do a principle called infinitesimal rotations. You take a magnetic state, you basically change a pair of atoms slightly, and then calculate the change of the total energy with respect to these small changes. And this gives you basically these Heisenberg and Jarodzinski-Moria parameters. And you can do that with different codes, for example, with the quantum espresso code. We are doing it with the Fleur code and the KKR code because we are more used to that code. Now, let me say one word about this energy functional. This micromagnetic energy functional I have shown here. Here's the exchange, the magnetic anisotropy, and, for example, external magnetic field. And the question which I would like to address is, I'm putting now in this micromagnetic energy functional a skyrmion, which I showed you before. And what I'm doing now is I take this skyrmion into this equation and scale a little bit the radius of the skyrmion and look at the stability of the skyrmion. So I take my skyrmion. I basically squeeze the skyrmion a little bit by basically scaling up the radius of this magnetization, or make it a little bit larger, this way or that way. If I do that, of course, if I do that, the energy depends somehow on this stretching parameter. You see here, you have here a first derivative square. Due to the scaling, this becomes 1 over lambda square. Then I have here, due to this dr square, a lambda square. And if I plot now the energy as function of this lambda, I see, what do I see? I see that the energy has a parabolar behavior as function of this lambda. And what you see is the minimum of the energy is at lambda equals 0. In other way, it means if you put your skyrmion in this micromagnetic energy functional, your skyrmion is squeezed to death when it doesn't exist because it has the radius 0. This changes in one dimension, because in one dimension, if you have structures in one dimension, this still scales like 1 over lambda square, but here you have something which depends only on lambda, scales only with lambda, and therefore you see your energy functional looks like something like it has this form. It has a minimum, and this minimum is actually your domain wall. So a domain wall is a stable object in one dimension. But if you add now the Dzielodziński-Moria interaction, which has this form of the chiral symmetry breaking, you get here an additional term which goes proportional to the derivative. And therefore, you have here in your energy function a different term, which is 1 over lambda. And this guarantees you a minimum. And that means the Dzielodziński-Moria interaction stabilizes these two-dimensional objects. Maybe I skip this part and come to the skyrmion radius. So we have studied this micromagnetic energy functional. What I can do now, I'm saying my skyrmion is anyway axial symmetric. It doesn't have to be, but I assume it's axial symmetric. And if I put now these axial symmetric conditions into my equations in the energy functional, I can ask myself, what is the optimal profile such that I can minimize? Which optimal profile minimizes the energy of the skyrmion? And if I do that, I'm coming to a skyrmion profile equation, which is terrible, complicated, very nonlinear, but I can solve it, for example, numerically by certain boundary conditions, saying that the spin inside the skyrmion points down and outside of the skyrmions, it matches to the ferromagnetic state. And what enters in this equation is a dimensionless parameter, which is basically this kappa, which depends on all these parameters, which I have first calculated by ab initio. And my equation is written in the units of this domain wall width, which I showed you before. And what you see is, this is the solution. This is the radius as function of this parameter kappa. First of all, you see not much. It is a very nonlinear functional. But if you zoom in into this kappa, you see small changes of this kappa, small changes of these material parameters give you large changes in this radius. This we have actually looked at. Now my time is a little bit short. I'm running out of time. I have done these skyrmion applications. A very important material stack to put these skyrmions into a reality is the magnetic multilayer. Because the magnetic multilayer offers you a great versatility, what you can do to massage the magnetic structure such that your skyrmion and all these properties which you need are at the right Curie temperature, at the right size, at the right stability. All the conditions which you want to have for a skyrmion in a technology, room temperature, fast speed, stability, all this can be massaged by such multilayers. So you need heavy materials like platinum, for example, or iridium for a large spin orbit interaction. You need ferromagnetic material, cobalt, for example. You have to organize this material such that your magnetization is perpendicular. Then what you want is the ferromagnetic layer should couple antiferromagnetically to the next layer. For this, we have an RKKY material. This should be antiferromagnetic to minimize the dipole energy, and so on. And you have choices of the thickness, the layer composition, the growth condition, and the coupling strength. And so you have a huge perspective available. And what we have done recently is we have calculated 14 different multilayers. So we have taken cobalt platinum, which is the technologically most important one, and varied 14 different elements here: yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, up to cadmium, copper, zinc, and looked which one produce room temperature, which one couple antiferromagnetically. For example, here those in gray couple antiferromagnetically, those in pink or pinkish orange, they couple ferromagnetically. And if you put all this together, we could calculate the skyrmion radius as function of the cobalt layers. You see, we can reproduce this very funky behavior where small changes of the cobalt numbers give you large changes in the skyrmion radius. And so if you want to say that, for example, I want to have a skyrmion radius of 10 nanometers, which is technologically good, maybe these compositions, depending whether you have copper, for example, 10 layers of cobalt would be, for example, an important choice for skyrmion radius at zero field. With this, maybe I should stop due to the time. Maybe I move on to here. Oops. I should thank all my collaborators, the bright young graduate students, PhD students, postdocs, and of course also senior people. And of course I benefited from all of them, in particular Gustav Bielmeier, Nikolai Kiselev, Samir Lumis, Yuri Mokrusov, but also Hongying Jia, Markus Hoffmann, all the skyrmion work, Gideon, who did the spirit code, Fabian Lux, who did a lot of work on the chiral Hall effect, on the chirality of the systems, and also on the skyrmion stability. I thank many organizations, but in particular MAX. Without MAX, we could not have our code on this level. And without MAX, we would not be able to enjoy our collaboration with the ESPRESSO group, Quantum ESPRESSO group. And with this, I thank you very much for your attention, and I'm happy to ask questions.
Thank you. Thank you very much for this very, very nice talk, very interesting. So I would ask us if there is some question from the audience here in Zoom. I think there was some question before. Maybe one can raise the hand and ask directly. No, okay. So please, Nikita.
Yes, hello, and thank you for your fascinating presentation. I just have a simple question concerning the beginning. You raised that the energy scale is just about 1 MeV. How about does this effect SOC survive at room temperature? And how about the magnon-phonon interaction? Does it affect, I don't know, the application? Is it destroy or is it sensitive to apply the magnetic properties for them?
The effect itself is indeed very small, but the Curie temperature itself, the effect does not determine the Curie temperatures in systems of 3 dimensions. So if you have a 3-dimensional magnet, for example, the Curie temperature is basically determined by the Heisenberg interaction and not by the spin-orbit interaction. And therefore, as long as your magnetic system has a Curie temperature, is below the Curie temperature, has a magnetization, the magnetocrystalline anisotropy is there. But I should like to mention that the magnetocrystalline anisotropy has a different temperature behavior than the magnetization. It becomes smaller faster. So the hardness of the magnetic hardness of the material is reduced faster. And that is, of course, a problem if you have put your, for example, if you have an electric engine in a car. If the car becomes warmer, the hardness of the material goes down, and maybe it does not perform so well anymore. And therefore, we have to have, therefore, there is a research development increasing the Curie temperature, making the material harder at higher temperature. Now let me come down to 2 dimensions. If you have a magnetic interaction, that if you have a 2-dimensional system, a strictly 2-dimensional system, which is totally magnetically isotropic, then you don't have a Curie temperature. The Curie temperature is 0. Then the spin-orbit interaction, which produces this magnetic anisotropy, stabilizes actually the magnetic phase against fluctuations. So it is, then it is a very important ingredient for a finite Curie temperature. And then you had a question about magnon-phonon. So the magnon-phonon, yeah, there is, so typically the magnon-phonon interaction, so the magnon-phonon interaction is the interaction where the magnon and the phonon hybridizes. This typically is an interaction between controlled by the Heisenberg interaction, which controls the magnons, sometimes also the dipolar interaction, which controls the magnon, and the phonon. The spin-orbit interaction does not play an important role here. But the spin-orbit interaction has a slight impact on the magnon dispersion, and maybe can shift the resonance of the magnon-phonon interaction.
Okay.
The answers the question.
There is another question from Amelia, please.
Hi. So are these skyrmions, do they tend to be stable at room temperature under normal conditions, or do these have to exist at like extremely low temperatures or something? Because I'm a first year. I'm probably not going to explain this intelligently, but the electrochemistry group I'm in has been seeing some very strange effects with our thin magnetic films that we don't know how to explain. So I find this very exciting, but I'm not sure if it's possible that we are accidentally creating skyrmions that are influencing our results.
You have skyrmions at low temperatures and you have skyrmions at above room temperature.
Okay.
Typically, if you work in the world of ultra-thin films, 1-layer iron or cobalt on iridium and platinum, your skyrmions are very small, maybe 3-4 nanometers. And typically, these films have a very low Curie temperature. So your skyrmion has a very low Curie temperature, maybe I say a number, 20 Kelvin. But if you go to these multi-layers, which I have discussed, you can easily have skyrmions at room temperature. That's not a problem. And actually, that is the motivation to do skyrmions at room temperature. But typically, skyrmions are larger, typically, say, 30 nanometers, 20 nanometers, 30 nanometers. So it depends a little bit, what is the size of the skyrmions your colleagues in the lab are seeing?
Thank you for the answer. So let's take a question from the streaming. Should we consider SOC for all 2D materials? I think it was related to surface effects for SOC.
I would say yes. I would say yes. SOC can be very important for 2D materials. Because some of these materials or many of these, not all, some of these materials, for example, contain selenite, telluride. These are, of course, heavy materials, and they are P materials, materials with P electrons. And P electrons are typically have very strong spin-orbit interactions. So I can easily imagine that such interactions are important. And in particularly, they changed the Heisenberg model to very anisotropic models, for example, like the Kitaev model. And therefore, I think the spin-orbit interactions are important, that they are always the dominating one. I cannot say it depends a little bit on the details. It depends also on the crystal symmetry. It depends also on your substrate.
Okay.
But you know, without considering it, would be dangerous.
Another question from the audience. Ignazio Martin, please.
Thank you. Thank you very much for this very nice talk. I'd like to know, could you comment on the stability of skyrmions against external magnetic fields, how the radius depends on the external magnetic field? I'm thinking on real devices where you want to stack the components as closely as you can, and you may have stray fields.
Yeah, okay, stray fields. You are right, you have stray fields. That's not good. The stray fields have the disadvantage of making the skyrmion larger. And we want to have small and compact skyrmions. So therefore, we try to avoid this stray field. One way to avoid the stray field is to work with these layered antiferromagnetic materials, which I was probably not very explicit in saying that. I was a little bit rushed at the end. So what you saw is I have this multi-layer stack. And in this multi-layer stack, you have ferromagnetic films, cobalt films. But the way you stack these cobalt films is that we stack them such that we have what we call synthetic antiferromagnets. So the one layer points up, the next layer points down, and we choose the intermediate layer such that this coupling is antiferromagnetic. So that we have certain stray field compensation. And this stray field compensation helps us to keep the skyrmion small. Another possibility would be to create a skyrmion in an antiferromagnet. That's also possible. But then the detection might be a little bit more difficult. Typically, if you apply an external magnetic field, your skyrmion is typically becomes, yeah. So the skyrmions which I mentioned to you had been skyrmions without external field. But sometimes you can add a small external field and you move a non-existing skyrmion into, or a non-existing magnetic pattern into a stability regime of the skyrmion. Of course, if it's 5 Tesla, it doesn't help you very much. It is an academic. But sometimes you have your small bias fields, which you can implement in your multi-layer stack, might move you into the right corner of the phase diagram, where you can basically then stabilize your skyrmion under a bias field.
Okay, thank you. So Christian is asking something, please.
Yes, thank you. I want to ask Professor if the fact that R3 has solved the problem of spin electronic on Hamiltonian. What's the origin of the Basha effect? Is it a perturbation on the Hamiltonian, or the fact that R3 has solved the spin electronic in Hamiltonian have a correlation?
Sorry, I wasn't quite sure. I didn't catch your question exactly. Do you want to know about the origin of the Rashba effect, or?
Yes, sir. Yes, sir.
The origin of the Rashba effect is in some sense spin-orbit interaction plus symmetry breaking. So if you consider these two facts, Rashba symmetry breaking plus spin-orbit interaction, then you can basically derive per perturbation theory and contribution to your Hamiltonian, which is the Rashba effect. But the symmetry breaking cannot be arbitrary, because there is a, depending on your symmetry breaking, you have either the Rashba effect or the Dresselhaus effect. For example, if you have a symmetry breaking, like the symmetry breaking of a surface, which have, say called C2V, C4V, this type of point groups, then you get a Rashba effect. But if you have a different type of symmetry breaking, like D2D, then, which is typically for gallium arsenide, for example, so that you have a broken bulk inversion, then you get a different type of spin-orbit Hamiltonian, which is the Dresselhaus Hamiltonian. So if you have structure inversion symmetry breaking, you get a Rashba. If you get, if you have bulk inversion, you get a Dresselhaus. Both of them are linear in spin-orbit interaction. Yeah. And you can get more complicated things depending on your symmetry in orbitals.
So, Stefan, there is a question from the streaming. Can you please comment on the role of SOC in designing the photomagnetic systems? So back to the previous comment.
In which systems? In?
Photomagnetic system. That means manipulating spin through light pulses.
Yes. Here is, of course, the light enters basically as a vector potential, and the vector potential couples to the spin. And through the spin to the spin-orbit interaction, to the lattice. That is my picture.
Okay. I think we can get this last question. So when we put non-magnetic material on top of a material with large spin-orbit coupling, does the strength of Chelsinski-Moria interaction depends on the thickness of each material?
I showed in the talk the dependence of the Rashba strength as function of the depth. And you get exactly the same behavior for the, not the identical behavior, but an analogous behavior to the Chelsinski-Moria interaction. So if you have, for example, a magnetic material in the vicinity of a material with strong spin-orbit interaction, so the wave function of the electron of cobalt, of the magnetic materials, moves, the electron hops to the platinum and maybe hops back and produces the Chelsinski-Moria interaction. But the deeper it hops, the less is the contribution. So that means maybe the first platinum layer contributes most, then you have additional contribution from the second, from the third, from the fourth, from the fifth. But the contribution, the deeper you are, the thicker you go, the less is the additional contribution. And sometimes you have also a slightly oscillatory behavior. So maybe the first or the second platinum layer did add to positive gelatin schema reaction. The third platinum layer has a negative sign, but of smaller amplitude. It's like an RKKY interaction in the DMI contribution.
Okay. Okay, I think we can stop here, and we really thank Stefan for this wonderful talk and for all these explanations. So thank you very much once more.
It was a real pleasure. I really enjoyed it. Sorry, I mismanaged the time a little bit. Okay, sorry about this.
It was okay, okay.
Yeah.
So thanks. See you soon.
Yeah. Have a great time. A good next week.
Yeah. Thank you.